This is SpaceTime, Series 21, Episode 11, for broadcast on the 9th of February 2018. Coming up on SpaceTime, a new study challenges popular theories about dwarf galaxies, a new theory to explain the discovery of matter in hostile black hole winds, and NASA goes for gold. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Existing hypotheses about how dwarf galaxies are spread across the universe is being challenged following the discovery of a plane of dwarf galaxies orbiting around Centaurus A. The findings, reported in the journal Science, challenge the long-held idea that there are thousands of dwarf galaxies in all directions around large galaxies, sort of like bees swarming around a hive. Unusually, however, dwarf galaxies appear to orbit in planes around both our own galaxy, the Milky Way, and our nearest big neighbouring galaxy, Andromeda. And that's led astronomers to consider both the Milky Way and Andromeda as unusual outliers compared to most other galaxies in the universe. However, this new discovery means that dwarf galaxies are distributed in planes that are almost perpendicular to the disks of the Milky Way, Andromeda, and now Centaurus A. And all that can't be a coincidence. One of the study's authors, Associate Professor Helmut Jurgen from the Australian National University, says it now seems the Milky Way and Andromeda are normal galaxies after all, and spinning pancake-like systems of satellite galaxies are far more common than previously thought. The problem is, even the best cosmological simulations struggle to explain the phenomenon of these small galaxies revolving in one direction around bigger host galaxies. It's now thought that most large galaxies have close encounters or mergers with other galaxies, and so co-rotating dwarf galaxy systems could form during these gravitational interactions. In this scenario, those dwarf galaxies would be devoid of dark matter. The Milky Way and Andromeda are both spiral galaxies, while Centaurus A has both elliptical and spiral features. The best-known dwarf galaxies around the Milky Way are the Large and Small Magellanic Clouds, which are visible with the unaided eye from the southern hemisphere. But scientists have identified close to 50 dwarf galaxy candidates around the Milky Way, and most of them are aligned in a plane orbiting around the centre of the Milky Way. Most of the dwarf galaxy candidates Jurgen and colleagues found around Centaurus A are also arranged in this fashion. And it's a similar case for at least half of the satellite galaxies orbiting Andromeda. Jurgen says these new findings will have major implications for future cosmological research.
Well, basically, the paper is about testing predictions of the best model we have for our universe today, which is called the Standard Model of Big Bang Cosmology, with the help of so-called dwarf or satellite galaxies. So there are galaxies that are much smaller than the usual galaxy we know, the Milky Way and Andromeda. And there are two fundamental predictions that this standard cosmology model makes when it comes to environments like our Milky Way. And these two predictions are, first of all, the Milky Way-sized galaxies should have thousands of small satellite galaxies just flying around it. And these satellite galaxies should be distributed randomly in space around the host galaxy. So they are like flying around like the bee swarm around the beehive. So that's a bit the picture that you can that you should keep in mind when you look at predictions from the cosmological model.
And that first one's already a problem because when we look around, we haven't found thousands of dwarf galaxies. There are a few, but not thousands. And so that's got to set alarm bells off to start with.
Already, yes, exactly. I mean, the theoreticians and the galaxy formation evolution people, they can get around this. I can iterate on that a little bit further later on. But I just want to basically address the second point, namely that these satellite galaxies should be randomly distributed in space and that they are flying in all directions, because that is related directly to what we have shown is incorrect in the case of Centaurus A. So basically, as a result of 2 decades of research effort across the world, the observers, the observation astronomers, they showed convincingly that these satellite galaxy systems around the Milky Way and the nearby Andromeda galaxy contradict both of these predictions. You already mentioned the fact that there are not thousands of small galaxies around the Milky Way. So that is already a major concern. And the second concern is that these satellites around the Milky Way and the Andromeda Galaxy are distributed not randomly, but they are in a highly flattened, almost plane-like cosmological structure.
That's got to say something about our understanding of cold, dark matter as well then, doesn't it?
Well, it shows basically that these best models we have cannot predict what we actually observe in the two best studied cases that we have, the Milky Way and the Andromeda Galaxy. It's a complete disagreement here. And this discrepancy between theory and observations led to a major crisis already 20 years ago. Because they were even the best, even today, even the best cosmological simulations, they were struggling majorly to explain this so-called anisotropy problem. That was the major finding. Now, for more than 10 years, the questions have gone unanswered whether now these results from these most powerful high-performance computer simulations in the world are actually correct. In other words, branding the Milky Way and Andromeda Galaxy as the odd ones out. Or the alternative interpretation is that the Milky Way and Andromeda are indeed, with the satellites, galaxies are indeed accurate representations of the typical galaxies in the universe. As a consequence, there must be a fundamental flaw in the current cosmological model. So these were the two possibilities. Now, in order to make progress in this field, the only way forward is to study a dwarf galaxy system around another galaxy, such as the largest galaxy we have in our local universe, the Centaurus A galaxy. Now, this sounds pretty easy and straightforward. Of course, everybody would do that straight away, but the difficulty is the technical aspect. It's very, very difficult to actually find these optically elusive satellite galaxies. And once you have them, you have to measure accurate distances and velocities. So that's quite a major task, and it took quite a couple of years to get to that stage where you can now look at another system outside of the local group, Milky Way and Andromeda Galaxy, and try to understand what's going on in another major big galaxy. And once these quantities were measured, we found two interesting results, which are now covered by this science paper. Namely, the satellite galaxies around the Centaurus A galaxy are also distributed in a highly flattened cosmic structure, similar to what was found around the Milky Way and Andromeda. And what was even more striking was that what we found is that the satellites are streaming in the same direction in that plane. So you can imagine already like on a carousel, they are orbiting around the host galaxy and flowing in one single direction, almost perpendicular. So you have this nice, beautiful dust lane, and it actually is almost perpendicular to that dust lane.
Okay.
So when you look at an image, you can imagine that the galaxies, the dwarf satellite galaxies that are in the northern part of Centaurus A, they are coming towards us, while the satellites in the south are moving away from us. So this is a real sign of rotation that's along here. And what we found is essentially, if we do a careful analysis, this is a long-living kinematical supported cosmic structure. And the first evidence, and that is the key now, that there are these planes of satellites beyond the local group. So it seems that, after all, the Milky Way and Andromeda are normal galaxies, and the pancake-like co-rotating systems of satellite galaxies are much, much common than predicted by cosmological model. And this is finding now challenged the small-scale structure formation that in the prevailing cosmological paradigm. So that is a major move now. Basically, the ball is back now to the theoreticians to explain why we found in the three best studied systems, Milky Way, Andromeda, and Centaurus A, why do we find always this type of flattened satellite galaxy structures that are co-rotating around the host galaxy?
And also, I guess, why are they rotating the way they are, as opposed to, say, rotating with the disk through frame dragging or something like that? That's another issue.
Yep, absolutely correct. Yes. So I mean that is. I mean, so you end up basically with two major conclusions or major perspectives for future activities in the research. On the one hand, now you have this new result questions seriously the validity of the standard model on galaxy scale. We all know that on large scales, like gigaparsecs scales, the cold dark matter models are quite accurately describing what we observe in the galaxies. So that is also quite fascinating. So on large scales, it's really working. But when you look at the fine print of the cosmological contract, let's say, we see that individual galaxies are thus not behaving the way these very successful models are predicting. So the new results now basically, bring the ball back to the theoretical cosmologists, because they have now to seriously search and think about alternative cosmology models, maybe fine-tuning the existing models to explain the observed properties of satellite galaxies. So that is one aspect. And the other aspect that you were referring to, how they are actually rotating around the host galaxies, the origin of these planes. What is the reason why these satellite galaxies all rotating around the centers? And instead of having a cosmological origin, it could well be that these observed galaxies are actually the remnants of a major galaxy collision. One can imagine, for instance, a scenario that where an intermediate-sized galaxy is falling into Centaurus A or the Milky Way, for that matter, and gets destroyed by the tidal forces in the process. So when you look at, for instance, the Milky Way, we know all that, beautiful night sky here in Australia, the Magellanic Clouds are very prominent in the sky. And these could be the visible debris, the leftovers of such an event, in the case of the Milky Way. When you look at the Centaurus A galaxy, people who are familiar with the morphologies of galaxies, we know about the spirals, we know about the elliptical galaxies, but now Centaurus A has a little bit of a mixture of these both.
Yeah, it looks like a collision, doesn't it?
Exactly, absolutely right, exactly. And that is exactly a possible origin of this co-rotating system of dwarf galaxies, a signature of a major merger of another galaxy in the past. And so that is now what we are going to do in the coming years. We study now these satellites in more details, try to model what's going on, assuming other scenarios than the standard cosmology, and try to understand if there's a major merger as a result of this that led to these satellites rotating around the host galaxy. That's all very exciting new directions that we will pursue in the future.
That's Associate Professor Helmut Jurgen from the Australian National University. Centaurus A, or NGC 5128, is classified as either being a lenticular or possibly elliptical starburst galaxy in the southern constellation Centaurus. Starburst galaxies are so named because they're undergoing rapid star formation, and in the case of Centaurus A, this might have been brought about through a collision with a smaller spiral galaxy. Not only are astronomers still debating the type of galaxy Centaurus A is, but they're also debating its exact distance, thought to be somewhere between 10 and 16 million light-years. Whatever its real distance, Centaurus A is one of the closest radio galaxies to Earth. Radio galaxies have active galactic nuclei, or AGNs, indicating the presence of a feeding supermassive black hole in the galaxy's core. The one at the heart of Centaurus A is shooting out relativistic jets responsible for emissions in X-ray and radio waves. Scientists estimate this black hole to be about 55 million times the mass of the Sun. By comparison, Sagittarius A star, the supermassive black hole at the centre of our own Milky Way galaxy, contains only about 4 million solar masses. I'm Stuart Gary. You're listening to SpaceTime. Okay, let's take a break from our show for a word from our sponsor, Physical Attraction. Physical Attraction is the podcast that explains physics one chat-up line at a time, discussing themes from the fundamental laws of nature to the various ways the world might end. You'll hear a mix of narrative episodes and interviews with scientists, scholars and authors. There will be thought-provoking discussion, stories from the history of science and explanations of the beauty of physics. You can find the show on Apple Podcasts or wherever you listen to podcasts, and on Twitter at PhysicsPod. And you can visit the website and download all of the past episodes at www.physicspodcast.com. That's www.physicspodcast.com. And we'll include the link in the show notes as well. That's Physical Attraction. Check it out today. And now it's back to the show. Scientists have developed a new hypothesis to try and explain the origins of molecules discovered in the destructive cosmic outflows produced by supermassive black holes. The idea, reported in the monthly notices of the Royal Astronomical Society, is that new molecules are being produced in black hole winds. If correct, it could explain how stars can form in these extreme environments. However, scientists will have to wait until the new James Webb Telescope flies sometime early next year before they'll be able to test out the idea. The existence of large numbers of molecules in winds powered by supermassive black holes at the centres of galaxies has puzzled astronomers since they were first discovered more than a decade ago. You see, molecules trace the coldest parts of space, and black holes are the most energetic phenomena in the universe. So, finding molecules in black hole winds is a bit like discovering ice in a furnace. Astronomers questioned how anything could survive the heat of energetic outflows. But the new hypothesis by Alexander Richings from Northwestern University predicts that these molecules are not survivors at all, but brand new molecules born in black hole winds with unique properties that enable them to adapt and thrive in this hostile environment. Richings and colleagues developed a computer code which for the first time modelled the detailed chemical processes that occur in interstellar gas accelerated by radiation emitted during the growth of a supermassive black hole. When a black hole's wind sweeps up interstellar gas from its host galaxy, this gas is heated to extreme temperatures, destroying any existing molecules. By modelling the molecular chemistry in computer simulations of black hole winds, Richings and colleagues found that this swept-up gas can subsequently cool and form new molecules. The new idea answers questions raised by previous observations. Back in 2015, astronomers confirmed the existence of energetic outflows from supermassive black holes. These outflows kill everything in their path, expelling molecules that fuel star formation. These same winds are also thought to be partially responsible for the existence of so-called red and dead elliptical galaxies, in which no new stars are forming. Then in 2017, astronomers observed rapidly moving new stars forming in these winds, a phenomenon many thought impossible given the extreme conditions in black hole-powered outflows. The new theory means black hole winds destroy molecules upon first collision, but then forms new molecules, including hydrogen, carbon monoxide and water. The authors predict the new molecules being formed in these winds are warmer and brighter in infrared radiation compared to pre-existing molecules. That idea will be put to the test when NASA launches its James Webb Space Telescope aboard an Ariane 5 rocket next year. If correct, the telescope will be able to map black hole outflows in detail using infrared radiation. You're listening to Space Time. I'm Stuart Gary. Arianespace has set up an independent commission of investigation chaired by ESA's Inspector General after its first launch for the year placed 2 telecommunications satellites into the wrong orbits. Arianespace Flight VA 241 appeared to blast off normally aboard their Ariane 5 ECA rocket from the Kourou Space Centre in French Guiana. However, as the ascent to orbit continued, ground tracking stations lost contact with the Ariane 5 some 9 minutes and 26 seconds into the mission. It soon became clear that the mission had deviated off its flight path soon after launch, although that wasn't mentioned in the launch coverage. Mission managers struggled to re-establish contact with the spacecraft, eventually confirming that both satellites were deployed successfully but into the wrong orbits. Both satellites are now operating normally and should be able to reach their intended geostationary orbital positions. However, both will need to use more fuel than expected, resulting in shortened overall lifespans. The first of the payloads released was the SES-14 telecommunications satellite. Built by Airbus Defence and Space on an E3000 electric orbit racing platform, it's designed to provide satellite communications across Latin America, the Caribbean, North America and the North Atlantic. It uses a combination of C and Ku band wide beam transponders as well as Ku band high throughput spot beams. SES-14 has also hosted a NASA science payload. The Global Scale Observations of the Limb and Disk, or GOLD package, is designed to study Earth's thermosphere and ionosphere to improve science's understanding of how the sun and space weather affects the upper atmosphere, causing it to expand and contract. It's designed to study the interface boundary region where Earth's rarefied upper atmosphere meets space. This is a critical layer, impacted by both terrestrial weather from below and space weather from above. The atmosphere in this region gets compressed during solar storm activity by pressure from the solar wind of charged particles being emitted by the sun. These ionized particles produce geomagnetic storms capable of overloading and damaging, even destroying electronic circuits on spacecraft. Alternatively, when the solar wind is low and not compressing Earth's atmosphere, the atmosphere tends to expand further outwards, slowing down satellites and causing them to experience orbital decay. This forces mission managers to use up more fuel to maintain a satellite's correct orbit. And the more fuel you use up, the shorter the satellite's life will be. As well as affecting spacecraft and astronauts, space weather also impacts terrestrial power grids and communication systems on the ground. Being attached to a communication satellite means Gold will study space weather from geostationary orbit 36,000 kilometres above the equator. The launch anomaly has added at least 4 weeks to the time it takes SES-14 to reach its final orbital position. The Gold instrument will scan the entire Western Hemisphere every 30 minutes, making this the first time that scientists can track day-to-day changes in the upper atmosphere rather than its long-term climate. Put simply, Gold is essentially a bar-fridge-sized imaging spectrograph, an instrument which breaks down light into its component wavelengths and measures their intensities. The second payload released by Ariane was the Alya 3 telecommunications satellite, built by Orbital ATK using its new Geostar 3 hybrid platform. The spacecraft uses conventional chemical propulsion to reach orbit quickly, and then engages electric propulsion to maintain orbital position. Alya 3 will provide broadband communications across parts of Brazil and Africa. The United States has launched a new missile early warning satellite from the Cape Canaveral Air Force Base in Florida. The space-based infrared system GEO-4 is part of a constellation of satellites designed to detect and track enemy missile launches through their infrared heat signatures. The new spacecraft was blasted into geostationary orbit aboard a United Launch Alliance Atlas V rocket from Space Launch Complex 41. The Atlas V flew in its 411 configuration, which includes a single solid rocket booster, a Centaur upper stage, and a 4-metre payload fairing. The 4,500 kg GEO-4 is based on a Lockheed Martin A2100M platform, equipped with an infrared sensing scanner to monitor the full disk of the Earth for missile launches and an infrared starring sensor to detect smaller short-range missiles. The spacecraft carries enough fuel for an orbital life of about 12 years. The constellation involves 6 geostationary satellites. The project also includes infrared sensors mounted on several National Reconnaissance Office Trumpet-class signals intelligence satellites. These satellites are placed in highly elliptical Molniya orbits to observe the Earth's polar regions, which are difficult to cover from geostationary orbit because of the curvature of the planet. Speaking of the National Reconnaissance Office, it's launched a new spy satellite. The classified NROL-47 payload was flown from Space Launch Complex 6 at the Vandenberg Air Force Base in California aboard a United Launch Alliance Delta IV medium rocket. While the US government won't comment on classified missions, flights from Vandenberg usually involve retrograde launches which don't go over land, and usually end up in high inclination orbits that are impractical from Cape Canaveral, which is better suited to low inclination and equatorial geostationary orbits. NOTAMs, or Notice to Airmen, indicated that the Delta IV's second stage was to come down off the Antarctic coast, indicating an extreme southerly flight path. Based on the flight path details and the maximum launch capability of a Delta IV equipped with 2 GEM 60 strap-on solid rocket boosters, NROL-64 is likely to be the latest satellite in the controversial Future Imagery Architecture program. While further optical reconnaissance satellites in the program have been shelved because of massive cost overruns, the radar reconnaissance component known as TOPAZ is continuing. TOPAZ are designed to be successors to the earlier LaCrosse Onyx radar satellites. 4 of these 8-ton Boeing-built TOPAZ satellites are already in orbit. These spacecraft use advanced synthetic aperture radar systems to image the Earth's surface day and night and in all weather conditions. This latest satellite, TOPAZ 5, is also likely to be the first of a new improved Block 2 spacecraft, which will fly at higher inclination orbits at altitudes of around 1,500 kilometres. Now, speaking of spy satellites, Beijing's just launched 3 more signals intelligence satellites for the Chinese military. The Yaogan Weijing 30 Group 4 satellites were placed into a 600-kilometre high orbit aboard a Long March 2C rocket launched from the Xichang Satellite Launch Center. Beijing euphemistically describes the satellites as part of a remote sensing mission used to conduct electromagnetic and other experiments. And they're sort of right, because what the satellites are actually doing is searching for signals intelligence data from foreign powers. This latest flight follows the launch of 3 identical satellites on December the 25th, and it brings to 12 the number of these satellites now in orbit. The final constellation is expected to include 18 satellites, with the remaining 6 to be launched in 2 groups of 3 later this year. And time now for Alex on Tech, looking at wearable ID devices. First, we had plastic credit cards pushing into the domain of regular cash. Now it seems the credit card itself may soon be replaced by new wearable ID devices. Financial institutions are now introducing electronic ID you wear as a ring. So, does this mean it's a case of one ring to rule them all? one ring to find them, one ring to bring them all, and in the darkness bind them. With the details, Alex Zaharov-Reut from IT Wire.
Yeah, this is an interesting one. People have probably heard of payment wearables. I remember Visa doing something with some sort of wristband, but the first payment ring in Australia has launched, and it's called Halo from Bankwest, which is one of the sub-brands of Commonwealth Bank, the biggest bank in Australia. And this ring, it comes in different sizes, so you can make sure it fits you, and comes in two different colors. I think it's white and a darker color, and it requires no batteries, no dedicated app, no charging, and it's waterproof to 50 meters. So you wear it, and it's linked to your MasterCard account, and so it's like using the tap and go on your card, or like using the payment ability of your smartphone or watch. But instead of having to have a device that you've got to charge or have with you, I mean, a ring is normally sitting on your finger, so you can sort of go out for the night, and anywhere that you can use tap and go, taxis, in shops, in nightclubs, anywhere that, vending machines, you can use tap and go. So this little device just allows you to wear the ring, and, as long as you've got money in your account, you can make payments just with that and nothing else.
Could be a problem if you're a member of the Yakuza, of course.
Well, that's right. I mean, the ring's not supposed to be transferable, but unlike tap and go card that comes in the mail, this will cost $39 Australian. They're selling it for $29 for a limited time to its customers. But it also heralds other forms of jewellery and clothing that will have, these little chips inside that will link to your account. If you lose the ring, you'll have to contact the bank and, have to say, switch it off. And just like a tap and go that currently exists with your card, you'll be able to make payments up to $99. And after that, you'll have to type in whatever the PIN number is. But it just means that if you're somebody who wants to go for a jog or a swim or, somewhere where you don't necessarily want to take your wallet or even your smartphone or watch, you can just have this ring on you and yet still be able to make payments. And it's one of those steps towards the cashless future that terrifies some people and excites others.
We're seeing the same sort of convergence in other areas too. The Opal card in Sydney and similar cards in Brisbane and Melbourne, which allow you to use public transport, they're going to be melded into an app for your phone.
What actually has happened, MasterCard has done a trial with Sydney ferries, and for the past several months, you've just been able to use your contactless tap-and-go MasterCard to pay for ferry trips. And this is something that will eventually be possible on all the world's various payment platforms. I mean, why should you have to carry yet another card with you when your tap-and-go card has the same sort of NFC or RFID chip inside of it that allows you to tap on and tap off at various locations?
ITY's Alex Zaharov-Reut reporting. You're listening to SpaceTime. I'm Stuart Gary, and that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through Apple Podcast iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from SpaceTimeWithStuartGary.com, or from your favourite podcast download provider. SpaceTime's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world on TuneIn Radio, and as part of Virgin Australia's in-flight entertainment. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary, at SpaceTime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/SpaceTime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.
Look into his eyes. They're the eyes of a man obsessed by sex.
You and I are going to get together and take things to the fully degenerate limit.
They called them in a bygone day.
Are you in a state of ill-defined energy? Because I know a few superpositions. I want to be your asymptote so I can get arbitrarily close to you. Disturbed? Concerned? Maybe a little bit intrigued? Physical Attraction is a new podcast where your host will attempt to explain concepts in physics, one chat-up line at a time. Find us on iTunes or wherever you get your podcasts, and on Twitter, @PhysicsPod. See you soon.
Hi, folks. Want to hear something funny?